Good afternoon, good morning, and welcome to C2 Smart's webinar today. Thank you for joining us. This webinar is brought to you by C2 Smart, a US DOT Tier 1 University Transportation Research Center. Today, we're joined by Dr. Simon Zhou, who will present old models with new tricks, bridging the gap in Bureau of Public Roads BPR functions with a cross-resolution perspective of theoretical fundamentals and emerging applications. So before we get started, just some quick notes. We'll be recording this session and uploading it to C2 Smart's YouTube channel and website. We also encourage all of you to participate through posing questions to our presenter today. You can do so by pressing the Q&A button at the bottom of your Zoom window and entering any questions, which we'll take at the end of the presentation by Dr. Zhou. So today's presenter, Dr. Simon Zhou, is an associate professor of transportation systems at the School of Sustainable Engineering and the Built Environment at Arizona State University. Dr. Zhou's research focuses on developing methodological advancements in multimodal transportation planning applications, including dynamic traffic assignment, traffic estimation and prediction, large-scale routing, and rail scheduling. We have a longer bio of Dr. Zhou available on our website or his own website as well if you want to learn more from him and get in contact with him. But with that, I'll hand it over to Simon to carry us forward. Please go ahead, Simon.
Yeah, thank you. So let me share my screen. Okay. Let me make sure you are seeing the.
That looks great. Go ahead.
Okay. So thank you for this special invitation by C2 Smart. And it's really my honor to be invited to present our recent research work. And our presentation is all about connecting our modeling community, and we will present a cross-resolution perspective. In the outline, we will discuss importance of volume delay function, VDF, for transportation modeling, and then we try to also explain the limitation of static BPR function. And then we try to see when we evaluate emerging technologies such as CAV, congestion duration, time-dependent flow control, how we can still use the BPR in the best way, theoretically consistent with the Macroscopic model. And then we will present 4 case studies, including New York City, and then we will talk about our future research directions. So as you know, the static traffic assignment is one of the very fundamental modeling component in our transport modeling area. And then the volume delay function, typically, will use the average travel time as a function of, allow me to read this a little bit more precisely, positive, nonlinear, strictly increasing function of volume delay. And we also define the volume to capacity ratio to drive all these travel time calculation. We have 2 parameters, free flow travel time based on free flow speed and the practical capacity. There's many forms of volume delay function. As you can see, one of the major early BPR function has a 4th order polynomial form, and we do also recognize there's a Davidson's model for signalized intersection. So the common understanding on the limitation of BPR, and in our research area, we typically will describe BPR with a difficulty in capturing Q evolution, building up, propagation, and then we also have the understanding the BPR is not readily available to model the bottleneck with a low flow rate but higher travel time. So that's why we try to, in our area of the research in the network modeling in general, we try to introduce dynamic traffic assignment, try to capture Q spillback, try to really represent multiple origin destination flow with more complex freeway merge diverge representation. And then we also try to highlight what we really need is 3 important criteria here. All those models should be theoretically rigorous. They should be numerically reliable in calculation, and also we want to have a computational efficient algorithm for sure. Over the years, in my team, we have been developing a number of open source education research software packages. One of the Python package developed by our ASU team is OS into GMS. At the current stage, we have 55,000 downloads, and which we will be able to convert the OpenStreetMap data to this GNNS, General Network Modeling Specification format for every city in the world. And also we develop a number of open source computational engines in C++, in Python, try to really enable different modeling tools for many different models here, such as a simplified kinematic wave model. I don't need to coupling model. I don't need to read the long list. Here we have challenges. The challenge is we always try to look at, should we use static chapter assignment or dynamic chapter assignment? Static chapter assignment has its own advantage of computational efficiency, what is easy to implement, but they are unable to capture the flow dynamics. But dynamic chapter assignment, on the other hand, is restricted by its complexity. And also practically oriented question. When we look at the BPR function, we have alpha as a 0.15, we have beta at the exponent with a value of 4. What does that really mean? Do we have physical implication of these two parameters? So I think in our community, we have many related questions. So that is why one of my friends, Norman, he sent a long email in the TMIP email list, and then I do try to document on all the wonderful conversations from our community. For example, one modeler would like to say the static chapter assignment should not be used on this in this case of freeway capacity planning, and it cannot handle overcapacity. But on the other hand, some modelers might argue all models are wrong, but some are useful, and then we always recognize that DTA has a very high input burden. On the other hand, DTA is very useful to provide all the dynamic traffic results. So I don't want to read all this list. I want to show our perspective. Our perspective here over the years, over the last 5 years, we have been looking at this DTA versus BPR or volume delay function from our fresh perspective. We try to introduce the perspective of bottleneck discharge rate very carefully, and then we look at the Q evolution, not only for just a stochastic Q model, we also look at the fluid Q, and then you will see how we try to introduce polynomial arrival fluid Q, try to link the average travel time together with the underlying traffic dynamics. Here we go. I try to just present the fundamental challenges in our volume delay function, and then I try to list them in the following category. So number one is, how do we understand flow and capacity, particularly from a queuing perspective? The volume should not be simply just a throughput. It should be inflow volume, outflow volume, and the capacity should link to the discharge rate. Number two, how do we understand the dynamic nature and also the different aggregation level of the system? Because we cannot simply just define volume capacity for any horizon or for any analysis period. We also need to consider very carefully the analysis period congestion profile, which is related to our question number 3, okay, for the challenges of VDF modeling. And then, since we try to model the partially oversaturated flow condition, we do not have a readily available tool from the stochastic queuing theory. For example, AN1Q, typically they will assume lambda over mu lambda is the arrival rate, mu is the discharge rate, the lambda over mu is always less than 1. And in our case here, we need to understand how to capture this partially oversaturated condition. I have other challenges such as how to consider different type of vehicles, emerging applications, close resolution, but I still want to highlight these are 4 very fundamental challenges for us to think about volume delay function. After we conduct long review, we know that many research areas such as autonomous vehicle, mobility and service, public transportation, energy emission, there's a many important performance measure the stakeholder have their interest. And also, for example, if you look at equity, if you look at energy cost, as long as related to mobility or traffic congestion, we need to start with something very basic from the volume delay function or the volume delay, the demand supply interaction perspective. I also try to present the volume delay function is an aggregated view of the system. We can also look at car flowing or macroscopic view, which can link kinematic weight to the capacity or very detailed vehicle specific power to the discharge rate, to the driving profile. So we need to understand the different spatial and the temporal resolution for us to consider emerging technologies. I want to show the connection between different layers or different representations. So that is why I want to just go with you step by step to look at how we look at these different connections in practice and theoretically. I think we all learn from our textbook of transportation engineering. The practical linkage in the textbook typically is described as peak hour factor. It's used to convert peak hour volume to the 15-minute volume. And then we are using speed data to capture which hour of the traffic over the capacity. So by doing so, we have not been able to capture the congestion duration. So in this particular case, in the figure here, we had the busiest hour from 7:15 to 7:30, and then our congestion period who is standing from 6:45 to 8:25, and then the peak hour might be only just 7 a.m. to 8 a.m. So in this way, we need to carefully distinguish these different temporal volume definition. So I want to go a little bit forward. In this section 3, I try to introduce you a type of polynomial fluid queue model, and then try to help you understand in our transportation domain, we do have a lot of related approximation and thinking to define this congestion duration, to define the V over C ratio much more precisely. So let me start with this definition. So as you can see on my representation here, temporal axis, flow axis, this is a discharge rate mu. This is the arrival rate as a polynomial approximation. We can clearly define a number of time stamps. T0, the lambda equals to mu. T2, the intersection between arrival rate and the departure rate. And then we can also define the T3 as a Q dissipation. So in this way, you can try to just link T0 as the starting of the Q, T3 at the ending end of the Q, and then T2 as the highest Q. And then we can define the congestion duration as T0 to T3. With this common definition, we try to define the volume delay function as a loading ratio. The total D is total number of vehicles arriving at this congestion duration. At the current stage, the mu is defined as a constant discharge rate mu. I want to just introduce or reintroduce this Dr. Gordon Newell's classical textbook in published in 1982, Application of Cooling Theory. He was the first person looking at this polynomial approximation for the arrival rate. So he introduced this quadratic arrival rate, T0 beginning, T2 highest Q, T3 ending of the Q, and then he developed a number of analytical terms from here. Very importantly, we can define the Q of the T, the Q length of the time-dependent duration with a closed form formula. And then he even clearly identified the average delay, W, is a function of d over mu function. And then we have the exponent of the 3. And then this is very closely related to our alpha function, alpha parameter and the beta parameter. So by looking at this wonderful analytical derivation, I ask myself, why the limited application of this wonderful quadratic arrival rate formula in our area? The reason is, if we simply use a quadratic term, as you can see, this is a quadratic arrival rate, T0, T2, and T3. T3 is the ending time of the Q. We might have a negative inflow. And also the arrival rate as a quadratic form is not easy for us to approximate many dynamics in the real life. It seems to us this arrival rate of quadratic form is only usable for the mild traffic congestion. So starting a few years ago, we are working with different researchers, including Dr. Chen and a number of our research partners here, try to extend this fluid Q model with a cubic arrival rate. So it's very important for us to look at the factored form. We have T0, T2, and then we define a T3 or we define a T bar. So the factored form of the polynomial function, all those important time points are part of this polynomial factored function, T0, T2, and the T bar. I don't need to go through all the derivation. We do introduce some similar concept to map the alpha parameter and the beta parameter right here. So we were quite excited to look at this potential connection between the discharge rate and travel time function. More precisely, we introduce a parameter of the M. The parameter of the M try to map the congestion duration from T3 to T0 to T2 to T0. So here is the cooling built-in period. This is the entire congestion period. By introducing this oversaturation factor, we are able to derive many analytical functions. I don't need to enumerate all the factored form right here. If you're interested, you can look at the translation research policy paper we published last year. But again, there's still some connection we need to enable to link the static link performance function with the dynamic cooling model. One thing I want to say clearly here is typically we define the analysis period, and then all the functional form we have is for congestion duration P. Yes, we do have the closed form solution, and I want to highlight all the closed form solution is a two-way closed form, which means on average, we have average travel time function similar to the BPR function. On the other hand, we have time-dependent delay if we assume the constant discharge rate. The last highlight I want to show is since we have the Newell model, so the first in, first out property and the tight capacity constraint are always enforced. We still need one more bridge. Why? Because in typical volume delay function, we say D over C or V over C, D as the demand. In the polynomial model, we just introduced here, we have mu as the discharge rate. And also how we can convert the V to the D require some further thinking. So that's why recently we also published this paper to link polynomial arrival queue with a Q volume delay function in one of the newly established journal, multimodal transportation. I want to just introduce a few more steps very quickly. How we understand D over C. So the D over C equals to a conversion between the analysis volume and to its corresponding congestion period volume. How we can understand congestion duration? We try to introduce a sensitivity analysis term, try to show when the D over C ratio increased here, then your discharge rate on average will decrease. The step number 2 here, we try to use this time-dependent arrival rate or time-dependent waiting time formula to link the lowest demand. We introduce one more parameter, MSR, to connect the congestion duration to the average or the lowest speed profile. So as you can see, we still have a few more steps here. I will try to demonstrate very quickly to finish the connection linking polynomial arrival queue model with the BPR type function. I will go very quickly here. I already tried to show that peak hour is here. And we define the speed and the capacity. And then we can capture the overall volume. And then we can try to map correctly from the demand over capacity to the volume over capacity ratio. So here the demand, what we try to introduce is an inflow demand, not simply just a volume in the traditional BPR function. Step 2 here, we look at the overall D over C ratio we just defined. We look at its relationship to the congestion duration. So in this figure, D over C ratio as an x-axis, this is a congestion duration. We do see a very interesting elasticity form available, and the exponent here is 1.05. And then by using that, we are able to link the congestion duration with the overall D over C ratio. Step number 3, we also need to look at the speed reduction ratio, and then we introduce another elasticity term to further represent the mapping from the static world to the dynamic condition. Finally, we are able to link this time-dependent speed profile. As you can see here, this is our polynomial approximation. There's a few more mathematical details. I'm not going to just go over these for the wider audience, but if you are interested, please go back to one particular paper we just mentioned here to look at all the derivation details. So by doing so, we are able to link the time-dependent speed profile with the average D over C function. I want to just highlight, we are one of the early attempts try to link all these different dimensions together. So in this diagram, we try to show we can have a closed form solution. We have the explicit function of the capacity. We have a restricted storage capacity. We have complex node model, linker model. We can have the static model all the way to the fully dynamic model. So you can see BPR function in this corner. We have set transmission model, link transmission model, and then what we try to propose here is just one-way step forward for the polynomial arrival queue and with a volume delay function. You do see the Poncare model, other quasi dynamic model, other model was all in this two-dimensional representation. In this schema representation, we can try to show how this fundamental diagram should be calibrated, polynomial queue, and the realistic waiting time. So I think we have a number of models ready for us to further connect. So I think I present a lot of material on this mathematical derivation. It's time for us to move from models to real-world application. First of all, I have 3 empirical data sets. Data set number 1 from California, data set number 2 from the city of the Beijing when I take my sabbatical leave in 2019, and the data set number 3, the taxi data from New York City. We select one particular OD pair to study that. Then this is the spatial origin destination of the corridor. And for the New York City, we select the OD pair from Midtown Center of Manhattan to JFK International Airport. Let's look at the data set number 1, Los Angeles. From the PANS database, we have flow, occupancy, speed, and then we are able to map this queuing function to a polynomial queue, as we can try to see here. This is the bottleneck location. This is the arrival rate direction. This is the potential approximated polynomial representation of queue profile. In this case, we do see T0 is 1 p.m., T3 is 7:45 p.m. Very congested. And then we are looking at the speed occupancy profile, and then we calibrate the corresponding flow occupancy plot day by day. Finally, this is our discharge rate we calibrated for the whole corridor. So as you can see, the discharge rate here is close to 1,000 vehicles per hour per lane, much lower than the optimal capacity, typically 1,800 vehicles per hour per lane. And then we can also look at the queue profile we approximated for this whole corridor. We do have a good approximation accuracy. Let's look at the city of the Beijing. The traffic condition on this red ring is much more complex. So we select one major bottleneck to approximate it, but we do recognize there's still many challenges for us to address. These are bottlenecks starting from 7 a.m. all the way to 9 a.m. And since they have different end of the day restriction on HOV lane or HOT lane, and we have to develop a 2 peak period model to accomplish the different discharge rate and the different arrival flow pattern. Over there, we can look at the discharge rate in that bottleneck is highly dynamic. If we assume the constant discharge rate is not sufficient, on the other hand, you can see the discharge rate is around 900 vehicles per hour per lane, lower than what we have even in the Los Angeles case. The queue profile approximation is quite reasonable. Let's go back to New York City case. So here, since we have the taxis pickup and the drop-off data, so we need to convert this pickup time and the drop-off time to the cumulative arrival and the cumulative departure in the month of October 2018. So in this way, using our definition, we are able to define the congestion duration for almost 8 hours as long as we see the traffic delay for this OD pair. And then using these techniques, we are able to approximate the discharge rate mu as 34 trips per hour. This is our virtual queue for this OD pair representation. So having this different approximation, it will be very interesting to look at the arrival flow rate dynamics across 3 different regions. Los Angeles, quite flat. Beijing has high dynamics. New York City also have some dramatic demand transition over the day. We also can go back to the city of Phoenix here, look at 4 bottleneck locations. We calibrate the traffic flow model, and then we use our volume delay function. Finally, here is our approximation using our calibrated model. Alpha is close to 0.2. The beta is close to 1 or 2 in this newly developed function. Why? Because we have also already congested bottleneck corridor here, so the sensitivity of the D over C to the waiting time is not less significant. This is our calibrated congestion versus reduction of speed function. Then if we plot a 1 year of the data over this D over C and the speed profile function, and we can see that there are still a lot of variation. I would like to just really show you the results on our D over C ratio. The D over C ratio in this corridor, if you look at the weekday, is about 2 or 3. So this D is a total demand, C is hourly capacity, which means we have a highly congested corridor with almost 4 or 5 hours of congestion every day during the peak hours, peak period. And then this is our approximated time-dependent delay compared to the real life observation. So after I present this back to practice, how do we understand alpha and the beta? Now we know that alpha and the beta has a connection to this polynomial vehicular function. And then we should understand the capacity should not be simply defined. And the capacity typically in our speed and the volume function, capacity is right here. And then when we try to look at the volume delay function, this is our D over C ratio now. When the D over C equals to 1 or V over C equals to 1, this should be our capacity point. And then the D over C ratio curve can show as this particular mapping, okay, among congested and uncongested region. We also need to look at how we map peak hour factor to the D over C. So here I would like to have a special thank to Dr. Balazamo. He is a senior manager in the modeling and forecasting section at the Arizona Department of Transportation. By working with me, he finished a doctoral dissertation entitled of data-driven method for categorizing of this transportation performance model. So he established a framework to define region A, region B, region C, so that we can have a better mapping from the observable congestion in the fundamental diagram to these semi-observable or this carefully defined D over C ratio right here. So in our perspective, the D over C ratio greater than 1 is still observable, but we need to better define the congestion duration consistently with the Cuny model. So with this fresh perspective, I want to conclude my discussion using a few, maybe a long list of future research actions. Number 1, we look at all the emerging application of multimodal transportation network. So we are looking at the flexibility, railway capacity, bus accessibility. We hope we help you understand if we try to model all the existing emerging technologies, you should not simply just look at the simulation from the beginning. You should look at the aggregated capacity over volume or the volume over capacity. And then you need to look at how the different fundamental diagrams should be developed. Here I list a number of related CAV modeling area. Typically, we consider human-driven vehicle was autonomous vehicle. Look at the fundamental diagram. But I want to highlight we need to convert or make the connection from the fundamental diagram to the volume delay function so that we can use that for the larger scale, for example, best practice model in city of New York. I have a few more questions here. How we can understand these human-driven behavior model? So typically, within this Carfolin framework, reaction time tau, and the minimal spacing, human-driven was CAV with a reduced congestion, reaction time tau, and the minimal spacing. So if we can understand all this connection, we should be able to answer question number 2, to link the corresponding capacity more realistically, and then to map the congestion duration, and then to map the jam density more precisely. But on the other hand, if you simply use a fundamental traffic flow diagram, you may see this type of speed volume function. And then you can see in this right-hand side figure, typically for the volume delay function, we consider this as a nonlinear, smooth, a very smooth polynomial curve to map the discharge rate to the average D over C function. So I do see some gap for researchers to look at fundamental diagram only, not being able to map to the practical volume delay function. Another question here, if we try to enable the flow control, as we try to introduce in our early slides, if I have arrival rate and I have departure rate, if I'm able to increase my departure rate, and then I should be able to reduce my congestion duration. And then how we understand this reduction of congestion duration more analytically, this is a good question for us to understand before we go to the simulation-based study. On the other hand, in addition to the supply side scenario, by simply assuming CAV will increase the capacity, we should look at the demand side scenario. If we're able to just keep the discharge rate as the same, and then we enable the different tolling strategy, we can try to smooth this arrival curve. On the other hand, also enable the reduction of the queue. If we try to apply both demand side and the supply side strategy, we can reduce the mobility impact of traffic congestion. So all these consistent definition, unified framework requires further research. And I really hope in this conclusion session, I try to present this high-level view. We have emerging technology such as demand suppression techniques, such as reservation system, incentive regulation. Essentially, it's trying to smooth the arrival flow rate. We have active control. Essentially, we try to increase the discharge rate. And then we need to very carefully consider the land use impact and then all these multimodal combination. So we talk about the input, we talk about the output, we talk about the different resolution, and then we really hope in this talk, we convey our message. If we try to optimize the system performance, we need to consider both demand and the supply, both demand regulation policy and the supply building effort to make a better balance between all these different strategies. And then we need to have this control method to actively control the transmission system and then to really enable a much more consistent representation along the way. So my takeaway message today is, number one, the alpha and the beta turnout from my discussion, you might see they do hold some physical significance, and then they really correspond to the arrival and the departure curve in traffic flow. Number two, I like to just highlight the polynomial arrival rate offer a very simple but a very efficient way to understand traffic flow dynamics. And if you understand the Kalman filter, you understand the polynomial, is a very simple way for us to enable system dynamics representation. We further introduce Q-based volume delay function. We hope this will enable us to look at larger scale scenario planning. And by having the rapid computational time will allow us to model many a large number of scenarios in a congestion mitigation strategy. Number 4, we show the potential of using this model to evaluate emerging technology. Yes, I'm a developer of a simulation-based model such as DTA line, CN line, or SM2GMS network modeling tools, but I do advocate we should not simply think evaluating of emerging technology is only based on simulation-based study. We need to have analytical model as our starting point. Number 5, we need to understand the system dynamics connection with different fundamental diagram, the over-C ratio, and the stochastic tuning model. Finally, I want to just highlight the importance of having optimal control, feedback theory together to lead some other closed-form analytical solution to capture time-dependent delay for the better control of arrival and departure profile. In my last slide, I want to thank all the wonderful students at the ASU, and also I want to thank the special support from our UTC TomNet Translation Center. As you can see, TomNet indicates teaching old models with new techniques or tricks. And here I conclude with my presentation and welcome for any questions.
Thank you, Simon. That was a great presentation. As Dr. Zhou mentioned, please, we want you to engage. So use the question and answer button at the bottom of your Zoom screen to enter any questions. Or if you don't prefer not to type, feel free to raise your hand and we can call on, unmute you to engage with Simon directly. So either one, it works for us. Please enter your questions and he can take any questions now. So Dr. Osbe, do you want to kick us off?
Yeah, maybe I can start with some, few comments and something that I can ask Shashank. Thank you for an excellent presentation. This is really good, and it's really refreshing to see, to use what we already know and then improve upon that. Because I guess the fashionable thing to do is to forget everything that we did and start from scratch, which is obviously, I also use Newell's things from Newell's book in my class, which is really important. And sometimes students ask, "Oh, it's 1982. Why you're using this?" But science doesn't get that old that quickly. Anyway, so I think your last point, Shashank, about having better link models for control, especially feedback control and so on, is really key, is really important. And in the past we struggled with that, and I think your work will definitely help that. Also, embedding this kind of link performance models in traffic assignment rather than just depending on simulation is really excellent. So I think there's a lot of room to improve and validate these models. And I'm saying this not to you, to the students who are listening, because as you mentioned, there's a lot of things that we can do to take your wonderful work and extend it and validate it with data and so on. But one, general question that I ask, and feel free not to answer that. So you see, even at the link level, it requires a lot of painstaking work, like you did, to improve existing models and to get some realistic results. But now there is also this new type of models, MFTs, at the network level. And they're, very simple functions. And I always have this question in my mind, even if we have been struggling to create realistic models of this aggregate nature at the link level, are we a little bit too not uncareful or not careful when we use these very simplistic models to represent what happens at the network level. I mean, do we need to kind of think a little bit more about that, you know? So because I mean, I know how difficult it is to do at the link level. Now you're aggregating the whole network, and I mean, you're using like a very simplistic speed density type of representations. So what do you think about that? That's a general thing. I mean, not necessarily related to what you presented, but I think it follows that thinking, you know, that is it possible to have that kind of aggregate function at the network level, that simple, or do we have to do more work on it?
Yeah, Ken, thank you. Thank you for all your wonderful comments, and it's really an honor, to first of all being invited to present our work here. We do have some thoughts along this line. We look at in this figure here, fundamental diagram. There are many two-way connections. For example, fundamental diagram, when you have discharge rate as a function of the overall density of the model, and then here we are still assuming the discharge rate mu as constant in order to get analytical form. And on the other hand, we see cell transmission model is able to just break this corridor into many small cells. So my response, or I just try to advocate cross-resolution modeling. So I don't think just a simple fundamental diagram can cover many complex in the network, but aggregated representation will help us to really understand the overall impact. And since I'm coming from the transportation planning area, I do recognize typically we look at capacity constraint just by using a capacity equation using Lagrangian relaxation. Yes, over there, we want to just bring the all the different communities together. If they are able to look at this polynomial discharge rate and to really have this close form, they don't need to deal with all these complex Lagrangian multiplier in many sense. So I think what I want to advocate is a connection.
Thank you.
Thank you. Okay, we have Professor Jose Halguin-Veras with his hand up. So Jose, go ahead. You're unmuted.
Okay, Yusong, fantastic presentation. I have a question about the implications of using the traditional BPR function. And basically, that's in my I happens to get the copy of the 1964 report, and yes, I could not find any evidence of how this magic number 0.15 and 4 were estimated. And we cite this 1964 report, like we have cited them millions of times, you see. And basically, it's not like a surprise to me that basically you find that the numbers are not even close to 4. So according what my understanding is that you estimated values in the range of 2 for this exponent. And basically, what are the implications of this, let's say, for economic analysis? Because my sense is that we are going to be basically overestimating congestion and also overestimating the benefits of capacity increases. And basically, what is your take about what are the practical implications for decision making based on your insights?
Yeah, Jorge and Dr. Halguin-Veras, thank you for your insightful comments. I remember you sent me this almost 60 megabytes of the file for this old classical paper. Yes, what we found here maybe is through the calibration in Phoenix area, we have a relatively low beta 10, but this all related to this arrival rate profile and departure rate profile.
Mm-hmm.
Maybe we are considered either over congested bottleneck, so we don't have a lot of sensitivity in terms of connecting the congestion duration all the way to the average delay. So if we carefully calibrate this alpha and the beta, this will enable us to control the arrival rate time dependent time dependent departure rate much more close systematically. And I think the critical interpretation is not simply say, hey, beta equals to 4 can be interpreted. I think we need to go to different bottlenecks to look at, can we capture their day by day travel time dynamics and also the underlying arrival rate dynamics, and then how sensitive, if we have the different congestion duration or congestion level, how sensitive this arrival rate can be changed. So that was my response to your wonderful, insightful question.
Okay, thanks a lot.
Thanks, Jose. We have another question that came in. Dr. Zhou, you mentioned that the application of polynomial dynamics in combination with the Kalman filter. Could you explain that piece a little bit more?
Yeah, I think this is related to my reading with all these optimal control analytical DTA by Kant's early work. So if we just look at this polynomial approximation, we should be able to use first order model, second order model, third order model to represent the different system states, and then to enable the conversion of this Kalman filter transition matrix, measurement matrix. So I just want to show that these which order we have for the traffic system dynamics. In the BPR function, we simply look at this exponent as a 4, but on the other hand, you can see in the Kalman filter world, you might need to look at a different transition point along the time dimension. And these transition points are not simply just a discrete time, they should be continuous time. So I think this was my quick response to your good question.
Okay, thank you. So one more question. Actually, 2 questions. So could you please say something about, for a PhD student, how to get inspiration for new models, and what do we need to look at to get new knowledge, whether it's math, physics, or economics? More of a general question.
I think this is also a very insightful question. Me as a researcher in this area, I always feel that we need to look at how we can apply different models, back to the title here, to address the practical challenges. So for example, if we have, allow me just to go back to this figure here. If you look at the different metropolitan regions, we have to look at the way for us to mitigate the traffic, the way for us to categorize all the different traffic conditions using new data set. I think we are entering a new area of all this AI machine learning. We do see the challenges and the possibilities. If we are able, not just looking at this image as an image, if we are able to look at the underlying arrival rate profile, departure rate profile, we can really add our analytical elements into this traffic congestion. I do see some interesting paper just by scanning this profile as the images, and I will challenge them and say, how about you scan this profile, and you're not going to be able to really predict all the time-dependent spatial correlation easily. We need to understand the underlying analytical property.
And the second question is, for the traditional traffic flow theory, is there still room for further digging, and will it be replaced by machine learning perhaps in the future?
I hope in 5 or 10 years, this machine learning model will have the more physical meaning, or physics inspired machine learning, and then the physics is really captured by what we talk about here. If you send more incoming flow, you have this hard capacity constraint. We are not able to just simply use a machine learning model as is. We need to consider the physical and consider all these real life restrictions. And then I think this is a big message. Physics should be incorporated in machine learning model.
All right, great. So I don't see any more questions. If anybody else wants to squeeze a last one in right now, otherwise we're getting close to our end time anyway. So with that, I'd like to thank you, Simon, for your wonderful presentation and joining us today. As a reminder to everybody, this presentation was recorded and will be made available on C2 Smart's YouTube channel and website. And just as a last note, this webinar was brought to you by C2 Smart Center and USDOT's University Transportation Centers program. Thank you for joining us, and we hope to see you soon at our next webinar, which will be on May 16th. So thank you,
Thank
Dr.
you so
Zhou.
much.
Thank you for joining us.
That was an excellent presentation. Thanks a lot.
Yeah, thank you. Thank you.
Goodbye.